I'm very excited to virtually be here. I'd like to talk about Path Oblivious Heap. I'll start with the motivating example. Perhaps the most wanted application these days is privacy-preserving contact tracing. I'm aware that there are many wonderful proposals out there for achieving this, but today let's focus on a conceptually simple and somewhat generic approach. Here's the approach. Imagine that the user's smartphones collect location traces and encounters with nearby devices. They upload this information to a cloud provider, which promises to perform various analytics, including contact tracing, as well as mining patterns that can potentially help us mitigate the spread of COVID-19. Since these traces are highly privacy sensitive, a good idea is to encrypt the records before uploading them. Once we collect these encrypted records, the question is, how can the cloud compute on this encrypted data? There are various approaches, and one possible approach is to rely on a secure processor such as Intel's SGX. For the purpose of this talk, let's assume for the time being that Intel SGX is secure. We can imagine that the secure processor creates a hardware sandbox, and inside the hardware sandbox, there is a decryption key that can decrypt the data and thus allow computation. But as soon as any data leaves the sandbox, it'll become encrypted again. Therefore, as long as the adversary cannot break this hardware sandbox, your data should be safe. At first sight, this seems like a very secure solution, only that it isn't. It's well known that access patterns to even encrypted data can leak highly sensitive information. So what are access patterns? Imagine that you execute a program on the encrypted data. The sequence of memory addresses the program visits is called the access patterns. Why do access patterns leak information? Imagine in our contact tracing example, suppose the data uploaded form a graph of social interactions. And suppose now you're traversing along the edges of the graph. Then the access patterns can leak the graph structure. Access pattern leakage can manifest in various forms. Here's another concrete example, binary search. I want you to think about how binary search accesses data. First, you'd look at the middle element, and then depending on the result of the comparison, you either look to the left or look to the right. Therefore, although the data may be encrypted, if you merely observe the entire sequence of accesses during binary search, you can infer whether the element being searched is small or large. In this case, access patterns are obviously very leaky. Therefore, an important question is, how can we defeat access pattern leakage? There are two things that are important. First, we want provable security. And secondly, we care about efficiency. If we did not care about efficiency, there would be a naive solution. Essentially, one can scan through the entire memory every time there's a request. But this would incur, obviously, linear slowdown, which is prohibitive. So how can we solve this problem? Turns out that people cared about this problem even back in the 1980s. Back then, Goldrick and Ostrovsky proposed an amazing abstraction called Oblivious RAM, or ORAM for short. ORAM allows us to obfuscate access patterns and achieve security as strong as encryption. At first sight, this seems really counterintuitive. We know that we can encrypt data. How can we ever hope to encrypt access patterns, which are a side effect of the program's execution? Of course, behind the scenes, encryption is not what's really going on. What really happens is that we would permute the data in memory, and we shuffle them around as we access the data. Turns out, if you do this in a careful manner, you can provably defeat all leakage. Obviously, ORAM is a security mechanism, and like most other security mechanisms, there is a price to pay. The good news is that Goldrick and Ostrovsky showed that there is an ORAM scheme that incurs only log cubed slowdown with respect to the insecure baseline. So here n denotes the total number of elements you want to store in the ORAM. Now, if you compare this with the naive solution of linearly scanning through memory, this is obviously a lot better and asymptotically non-trivial. The bad news is that there is a log n lower bound, and this, seems like the price you just have to pay for the added security. I also want to mention that in the recent work, we showed that this lower bound can actually be matched. Specifically, we constructed an optimal ORM called Optiroma that is a log n times slower than the insecure baseline. Okay, so that's ORM, and one great thing about ORM is that it's generic. It can take any program and compile it into an oblivious counterpart, paying a log factor slowdown for the added security. So in this talk, we care about making the priority queue oblivious. Obviously, a naive approach is to take the generic ORM and compile an insecure priority queue, let's say the ordinary binary heap, to an oblivious counterpart. As we mentioned earlier, this compilation will incur log n slowdown, so the resulting oblivious heap will have log squared cost for every operation, including extract, min, insert, and decrease key. We want to be more ambitious. The log n ORM slowdown seems pretty good, but we want to do better. And therefore we ask, can we make algorithms oblivious without having to incur the log n slowdown? At first sight, it seems like I'm asking for the impossible because I just declare log n to be a lower bound. But keep in mind that the log n lower bound is only relevant if you insist on having a generic compiler that can compile any program to an oblivious counterpart. In practice, when we encounter concrete problems or classes of problems, we often don't have to go through this generic transformation, and therefore we often don't have to suffer from the log n slowdown. Okay, so our goal is to construct an efficient oblivious algorithm for the heap data structure. As I said, we want to avoid the generic ORM slowdown, and therefore we give a customized construction called path oblivious heap. It may sound too good to be true at first sight, but our algorithm is almost as simple as the ordinary binary heap, and we pay only a very small constant slowdown relative to the binary heap. Let's now dive in and see how path oblivious heap works. We maintain a binary tree data structure. Here the tree is not upside down. This is how trees are supposed to look like. Every node in the tree is called a bucket, and every bucket is just a finite array. Now, except for the root bucket, which has size log n, every other bucket has size 2, meaning it can hold up to 2 elements. There are 2 types of elements being stored in these buckets, real elements and dummy elements. The real elements encode actual information, whereas the dummy ones are just there for security. We will assume that everything in the tree is encrypted, so the adversary can only observe the access patterns. Every element to be inserted into the heap is a tuple. Where K stands for the key, we are going to compare the elements by their keys. V stands for a payload string, and P is important. P is called the path identifier of the element. The path identifier specifies a path from the root to some leaf, denoted P, in this case, the blue path. An important invariant we maintain is called the path invariant. It says that whenever an element is inserted, a random path is chosen for the element, in this case, the blue path. And then during the lifetime of the element, until it's later extracted, it can only be moved around along this designated path, and it cannot reside anywhere else. Now, besides storing elements, every bucket also stores a label called the subtree min label. This will help us support extract min later. The subtree min label is a pair consisting of K and P. K specifies the minimum key residing in the subtree rooted at the bucket, and P specifies the path on which this minimum element can be found. So in this example, the solid green bucket has a subtree min label that is a pair, the green K and the green P. It tells us that the minimum element in the green subtree is the key K, and it's somewhere on the green path leading to the leaf node denoted by the green P. Of course, the root also has a subtree min label. In this example, the root's subtree min label tells us that the minimum element in the entire tree has the key K, and it's somewhere along the blue path. Okay, now with the subtree min label, extract min is very simple, right? To extract the minimum element of the entire tree, I simply look at the root node's subtree min label. I figure out the minimum element is on the blue path. I then visit every location on the blue path, and I'm guaranteed to find an element with the key k, and this is promised to be the minimum element. I can then remove this element from the path, thereby extracting it. For simplicity in this talk, we can assume that all elements have distinct keys, but it's not too hard to generalize to the case when the keys are not distinct. As I remove the minimum element from the blue path, I will break the subtree min labels for buckets along the path. Therefore, I have to fix this problem by recomputing the subtree min labels along this blue path. This is simple. Basically, the blue leaf first updates its own subtree min label. This can be done by examining all elements in the leaf bucket. And then it's the parent's turn. The parent can update its label by looking at the labels of the two children and by examining all elements in its own bucket. So in this way, from roots back to the leaf, every bucket will update its subtree min label, and the entire path's labels can be updated in log n cost. So this is how we support extract min. We can now take a moment to reflect on the security. If every insertion chooses a random path for the inserted element, then essentially every extract min will go to a random path. Importantly, we want to make sure that insertion not only chooses a random path for the inserted element, but also does not disclose the choice of the path until the element is being extracted later. In this way, every extract min reveals a random path whose choice has not been revealed before. Now let me show you how to support insertion. Suppose I want to insert an element k comma v. I will pick a random path. In this case, the green path ending at the leaf node p. I will add the tuple to the root. And this inserted element can later be moved along this green path, but cannot reside anywhere else. Note that when I add the newly inserted element to the root, I did not reveal the choice of the random green path. Of course, we cannot keep adding elements to the root because the root will soon overflow. To resolve this overflow, we are going to introduce a background maintenance process called eviction. Essentially, every time we insert an element, we will choose two random paths and perform evictions on these two paths. The goal of eviction is to move elements towards the leaves as much as we can, but without violating the path invariant. Specifically, for each path chosen for eviction, I will pack the elements on the path as close to the leaf as possible, subject to the path invariant. Okay, and next I will call the update labels operation defined earlier to recompute the subtree min labels on the eviction path. We prove in our paper that with this eviction process, no bucket will overflow with extremely high probability. I won't do the proof here. More importantly, by tuning the root bucket size, we can make the failure probability as small as the probability of breaking encryption. Okay, so this is how we support insertion. And again, the important thing to observe is that the insertion touches only the root bucket and two random eviction paths. And therefore, insertion chooses a random path for the newly inserted element without revealing the choice of the path. And later on, when we extract the element, the path revealed there is fresh and uniform at random. So what is the cost of our scheme? I recall that extract min touches one path, and the insertion touches the root bucket and two random eviction paths. Therefore, both extract min and the insertion cost only log n, just like the ordinary insecure binary heap. What's even better is that our slowdown with respect to the binary heap is only 2 to 3x. I have not discussed how to support decreased heap, but essentially it can be supported in the same manner. Before I conclude, I want to quickly mention that there is an amazing prior work by Jafar Gholi et al. They also achieve similar and yet somewhat incomparable theoretical results. I will defer a detailed theoretical comparison to the paper. Their scheme has large constants and therefore is much more expensive in practice. And in many cases, their scheme actually performs worse than prior schemes that were asymptotically worse. To summarize, in this talk, you learned that although ORAM has a log and lower bound, oftentimes for concrete problems, you don't have to suffer from the log and slowdown. Oblivious Heap is a great example for demonstrating this. Besides the Heap, I also want to mention a related result that I'm excited about. In a paper called MPC for MPC, which appeared earlier in ITCS this year, we showed that any computation in the so-called massively parallel computation framework can be made oblivious with only small constant slowdown. So now what is massively parallel computation? It's a model that captures practical frameworks such as MapReduce, Hadoop, and Spark. And it would be very exciting to try to apply these techniques for real-world large-scale data mining problems. To end, I want to call your attention to our open source implementations available on GitHub. I did not have time to cover additional applications and evaluation results, but you can find the details in our paper. Thank you so much for your attention.